After we have considered construction of PCs, the principal components, which are in fact very special type of linear combinations of the original variables, we said that we are going to check the properties that we had stated in the very beginning, the desirable properties of the principal components. The first one of them was that the total variability present in the original data should be equal to the total variability in the principal components. So, let us start with our first property today, that is property 1. We have total variation of y, that is of the principal components, is equal to total variation of x. Now, at this point we are still talking about the p-dimensional vector of principal components. We have considered as many elements of this principal or we have considered as many principal components as there are the original variables, and we have also defined total variation as the sum of the diagonal elements of the corresponding variance covariance matrix. So, let us say that I have total variation of y. What is this? By my definition of total variation of y, it should be the trace of the variance covariance matrix of y. Now, we know that this is nothing but trace of the variance covariance matrix of y. And what is y? Well, y is nothing but, you know that y is, we have constructed the principal components in this way. Y is the linear combination, the first linear combination E1x, y2 is E2x, and similarly yp is nothing but epx. So, this is in fact, if I want to write the y vector, I can actually represent the whole thing. This is my y vector, the collection of these y1, y2 to yp in the column form, and I have this as e1, e2 to ep, all these are transpose, and I have this as x. So, this is, if you recall, that this is nothing but our P transpose matrix, because this the P matrix is formed, the columns of the P matrix are nothing but the orthonormal eigenvectors E1, E2 to EP. So, this is nothing but Px, which also gives me equivalently that x is equal to Py, but I can handle the situation with this relation. So, this is trace of nothing but covariance of P transpose x. Why do I do this? Because I know what is the variance covariance matrix of x, and trace of covariance of this matrix is trace of P transpose sigma P, because I have assumed, I have taken that sigma is the variance covariance matrix of the random variables x, and now I use the spectral decomposition of sigma in terms of p d lambda. So, this is p d lambda p prime. We know what are these matrices already, and since P is an orthogonal matrix, its columns are made up of orthonormal eigenvectors. This is nothing but trace of d lambda, and trace of d lambda is nothing but sum of lambda i's. This is I from 1 to p. And what is total variation of x? Well, total variation of x is total variation represented by the original data, that is x. Well, by definition it is trace of the covariance matrix of x, which is trace of sigma, and trace of sigma is nothing but trace of p d lambda p prime. I am again using the spectral decomposition of sigma, and I am using the fact that trace of AB is trace of BA. So, this is nothing but trace of d lambda p prime p. Now, p prime p being an identity matrix, I will have to consider only trace of d lambda, and which is again equal to sum of lambda I from 1 to p, giving me the property, proof of the first property, that total variation of y is in fact equal to total variation of x. The next one was, we said that the principal components y1, y2 to yp, they should be uncorrelated. So let us say this, the principal components so constructed, they are bound to be uncorrelated. So we have y1, y2 to yp are uncorrelated. We combine one more thing with this, with variance of yi, the ith principal component is the ith largest eigenvalue of the covariance matrix of X. Okay. So we have y1, y2 to yp are uncorrelated with variance of yi being lambda I. This is again very simple because we have the ith principal component yi is nothing but ei transpose x, and this is true for all I from 1 to p. So that if I really have to consider what is covariance between yi and yj, well, it is nothing but covariance between ei prime x and ej prime x. So this is in fact ei prime covariance of x and ej prime, and this covariance x is nothing but our sigma matrix, the matrix which is very important to us for calculation of eigenvalues and eigenvectors, and we use the spectral decomposed representation of this matrix to write ei prime with p d lambda, p transpose and ej, right, where the columns of p matrix, these are nothing but e1, e2 to ep. Once I realize this, I can also realize very quickly that, well, if I write this as ei transpose and here I have e1, e2 to ep, then I have a d lambda, and here I have transpose of this, that is e1 transpose to ep transpose and ej here. Now since ei's are orthonormal eigenvectors, I am only going to have a 1 in the ith position when this ei transpose combines with the ei here, so that 1 in the ith position and 0 elsewhere, d lambda, and then again I have, now this is important because this is in the ith position whereas this is in the jth position. So they are never matching, and as a result I have a 0, this is jth, and as a result I have 0 if, well, if I is not equal to j, and well, if it is equal to I is equal to j, so 1 is going to match with 1 here, and resultant element that is going to remain is this ith element of d lambda, and that is going to be lambda I if I is equal to j. So in one go I can prove, I have been able to prove that this proves that covariance of, which implies that covariance of yi, yj is 0 for all I not equal to j, and variance of yi, which is covariance between yi and y with itself, this is equal to lambda I. Okay. The next property that we talk of is property 3. Well, we know covariance between xi, xj is sigma ij, the ijth element of the sigma matrix. Have constructed multiple components in such a way so that the covariance between yi and yj, that is the covariance between the ith principal component and the jth principal component, is 0. They are uncorrelated. Now what about covariance between the original variable and principal component? Say I consider covariance between xi, any xi, and not just the yi, but say any yj. So let us look into that, because this relation, this covariance or this correlation coefficient that I am going to obtain from here is going to help me a lot in data interpretation. Okay. So this is the next property that we are talking of, that is covariance between xi, that is the ith original variable, and the jth principal component yj is eij root of lambda I by sigma ii. Now I know what is lambda I. It is the variance of the ith principal component, and sigma ii is the variance of the original variable x. But what is eij? Where eij is the ith element of the jth eigenvector, that is Ej. Right? This lambda is lambda j, not I, because I am considering yj here. So this is lambda j, variance of yj. This is sigma ii, variance of xi, and eij is coming from the jth eigenvector Ej. It is the ith element of that eigenvector. Okay. So again we start from the form of the principal component yj. Let us try to express it in terms of x, then we are able to use the known results, and yj is nothing but Ej transpose x. Okay. This is true for all j from 1 to p. And then I have to consider, so well I know y is again y1 to yp, and these are nothing but E1x to EPX. Right. So this is nothing but E1 transpose to EP transpose combined with x, and this is P transpose x. So I have y is nothing but P transpose x, P being orthogonal, I have x is equal to Py. And then if I have to consider, well, x is just like y, it is also p dimensional. I have x1, x2 to xp, and I simply have the p matrix here. If you recall, the p matrix is nothing but E1, E2 to EP. And now I am saying that I am denoting the ith element of the jth eigenvector by Eij. So I can open up all these vectors, right. So for E1, if I have to write the first element of the first eigenvector, I will write E11, then the second element of this column vector, I am going to write E21. So this is exactly how I write a matrix P, if P is nothing but, and then P is nothing but represented by this Eij, and I have E11, E21 in this way up to EP1, and finally the first element of the pth vector, pth eigenvector, which is E1p, then the second element of EP, which is E2p, and then I have the last element or the pth element of the pth vector giving me EPP, and then this is Y1 to Yp. Right. So this gives me a new representation of x. I can say that xi, if I consider the ith element of the x vector, it is nothing but sum of Eik, Yk, and k, the sum is over that common dimension, obviously it is p. So now if I have to consider covariance between xi and yj, well, I will have to consider covariance between xi, I am using this form of xi, this is sum over I, and for yj, I am simply taking yj. Now I can do this because I know already what is the covariance between any yk and yj. So it is simple for me to handle this. Now I know that covariance between any yk and yj, where k is not equal to j, is equal to 0. So if I open up this sum and consider the covariance with yj, the only term that will make a difference in this covariance, will make a contribution rather in this difference, is the pth term. That is, when yp comes, with the coefficient EIP. Others are all equal to 0 because I am considering covariance between yk and yj, and k is not equal to I. So, this is basically nothing but covariance between Eij, yj, and then this is going to give me, so this is going to give me covariance between Eij and Eik. That is the only part that is going to remain, and I have Eij with yj and yj. Rest of these are not making any contribution, and covariance between yj and yj is of course lambda j, and Eij remains as such, giving me Eij lambda j, because I know that covariance between yk and yj is 0 for all k not equal to j, and is lambda j if k is equal to j. So, I am using this relationship, and then I can also consider the correlation coefficient between xi and yj. This is covariance xi yj by root variance of xi times root variance of yj. I know all these, so I can immediately write this as Eij lambda j, and this is root of sigma I, and this is root of lambda j. So, this is giving me Eij with root lambda j by sigma I. Let us go back to the statement. Yeah, we had stated that. Now, we have to make a small correction again here. This is not actually the covariance, but in fact the correlation coefficient. The covariance being equal to Eij lambda j. So, if I consider the correlation coefficient between xi and yj, then only I get this full thing. Okay, so, from here it is clear that this element Eij, it plays a very significant role in the correlation coefficient between xi and yj, right, because its sign is going to determine the sign of the correlation coefficient. I have the rest of it is ratio of two standard deviations, always positive. So, its sign as well as its magnitude are very important for me to interpret the relationship between the original variables and the principal components. Yes, there are some more parameters which can be now checked from whatever we have obtained, and let us list down a few important of those parameters which are very useful for data interpretation part. The first one is, we can note down these as some remarks or some notes. Okay. So, the first one is the one that we have just done, that is Eij, that is the ith element of the jth eigenvector. This is proportional to correlation coefficient between xi and yj, and so the magnitude of Eij and sign also of Eij indicate how important is xi to yj, and this helps in interpreting, because after all these principal components that we have constructed, these are not some direct observable variables, these are linear combinations of a number of several variables. So, we have to give some interpretation in terms of the physical variables, and if we have a certain relationship like this, it becomes a little easier for us to give the interpretation as to how these are related. Okay. So, this helps in interpreting yj. The second one is the proportion Now, if you recall, we have not talked about one more property of the principal components which we said is very important, that is, though the total variation in x is equal to total variation in y, ultimately to make the whole exercise a fruitful one, I should have the total variation in y, it should be explained by a very few number of a total variation of a fewer number of the principal components. That is, you had recall we had written something like total variation in y is approximately equal to the variation in y1, y2 to yk, where k is a number which is much smaller than the true dimension p. Now, that we have not checked because that is going to come out from actual data. Only when we have data we can actually see that how this, what is the effect or what is the extent to which this has been, this approximation is effective. Okay. But before that I can also say that the proportion of total variability or proportion of total variation in x explained by the kth principal component, right. What is the total variation in x? It is sum of the eigenvalues, and the variation explained by the kth principal component is nothing but its variance, and that is equal to lambda k. So, the proportion of total variation in x explained by the kth PCY k is equal to lambda k by sum of lambda I from 1 to p. And what do we want? Ideally, we would like to have this lambda 1 by summation lambda k a very large number. This should be as close to 1 as possible. Then should come lambda 2 by sum of lambda i's, and in this way. Okay. As the value of k increases, we would like to have this factor to be smaller and smaller, so that I can stop at a small value of k and say that if I consider these many principal components, it is good enough for me to explain the total variability present in the data. Okay. Then again, it is not necessary that I have to consider the principal component in isolation, that I should say that 1 explains the highest variability, so I stop at 1. No, I can consider 1 and 2. 2-dimensional is also good enough for me. So, in that case I have to look at the total variability explained by the first principal component and the second principal component. So, in this way, that is one more parameter that is of importance to me is proportion of total variation in x explained by the first k principal components, that is sum of lambda I from 1 to k, and this is the total variation sum of lambda I from 1 to p, all of them. Okay. And then comes the important point that if I have sum of lambda I from 1 to k is approximately equal to sum of lambda I from 1 to p, then I will say, and that too for some small k, smaller the better, for some small k, then it is enough to consider the first k principal components, and the data dimension can be reduced to k. That was our goal, primary goal. The data dimension can be reduced as we consider a part of y, that is, as we consider now the k dimensional vector y1, y2 to yk, k is much smaller than p. Okay. Now one thing is we have to be careful about, sorry, this is number 4 after the first 3 points. One thing we have to be careful about, we are saying that Eij is a very important factor for me to explain the importance, the association between Xi and Yj. Now if I have the data, Eij is essentially the ith element of the jth eigenvector. Now if I have the data which are in different units of measurement or data which have very different and very wide ranges of variation, then if I consider the data as it is and then focus on these Eijs and other measures, then the comparison would not be truly correct. What we have to do in such a situation is we have to try and make the measurements unit free, and so that we get the true picture of association. Okay. So this point also to be noted down before we actually do the exercise of that. So standardizing the variables. So in case the units of variables, units of measurements of the variables, so the units of variables are different, or the variables which is bound to happen in practical situations. We shall consider variables from different fields which are bound to have different units of measurement, and they can also have a totally different and very high range of variation. So this we should or the variables have widely varying ranges. We should obtain principal components from the standardized variables. So standardizing the variables means essentially we will have to divide we have to first take the difference of these variables from the corresponding means and divide by the corresponding standard deviations. Now initially when we working with the raw data, the matrix of importance to us was the variance covariance matrix of X, that is the sigma matrix. Now you can easily realize that if we standardize the variables, the whole matrix of importance to us is now the correlation coefficient matrix of the variables. Okay. So now we have to everything is getting replaced by the correlation coefficient matrix rho, which initially where we worked with the sigma, the covariance matrix sigma. Now our matrix of importance is the correlation coefficient matrix rho. So this is obtained from standardized variables, and we have to consider work. Can put it like this, work with the correlation matrix instead of the covariance matrix. Now question remains that will the principal components be same if we work with the sigma on the rho matrices? The answer is no. In general, the PCs derived from sigma and rho are different, right? And now we consider calculation of principal components from the correlation matrix. So I have principal components derived from correlation matrix. We really do not have to do much here. We will see that how a simple transformation helps us, and we will get all the results immediately from the ones that we have already proved. Okay, so first is we consider the standardized variables, that is the first step. and use a very general notation Z for those. So, I say that Zi is nothing but xi minus mu I, that is the mean of the ith random variable. We had earlier said that the mean vector, well, if you have to write the covariance, the term for covariance with in terms of expectation etc., we will have to use this mu being the mean vector mu1 to mu p. Right. So, we have, and sigma, the variance covariance matrix is sigma ij. Right. So, this is xi minus mu I by root over sigma ii for all I from 1 to p. There are p variables x1 to xp. I define p standardized variables z1 to zp, and now I just define a new matrix V, define V, which is nothing but diagonal of the sigma diagonal elements of the sigma matrix. So, this is diagonal sigma 1 1 to sigma p p, right. And then, well, I have Z. How can I write this Z vector? Z vector is nothing but Z1 to Zp. Right. In terms of the x vector, if I have to do it, well, it's simply that now that I have defined what is V and the diagonal elements are all positive. So, V is a positive definite matrix. I consider the inverse square root of V by spectral decomposition, by spectral decomposition of sigma. This is good enough to give me this also, V square root inverse of V, and then rest of it is nothing but x minus mu. So, I combine all these standardized variables in this Z vector in this fashion using x's, mu's and these elements sigma I, root sigma I coming into the picture in this way. So, now that I have Z is this, so what is expectation Z as expected, because I have standardized these and got Z. So, this is nothing but the null vector, because expectation x is mu, and what is covariance, variance covariance matrix of Z? Well, this is V minus half covariance of x minus mu, which is same as covariance of x, which is sigma, and then this is V minus half again. And what is that? Well, if sigma is the variance covariance matrix or the dispersion matrix of something of x, right, and you have these are getting divided by these, the ijth element of sigma matrix, by what is it getting divided? Well, it is getting divided by this, the element here, that is it's getting multiplied here by sigma ii raised to the power minus half, and on the other side it's sigma jj raised to the power minus half. So, in effect I am getting nothing but the correlation coefficients rho of xij, right. So, rho is nothing but rho ij, and what is rho ij? It is the correlation coefficient matrix of xij. Call this as rho ij, the matrix of correlation of xi and xj. Well, this was the matrix of covariance between xi and xj. So, you may write it xi xj as a subscript, but there is no need actually. Just like we have sigma as covariance between xi ij, and rho is the correlation matrix between xi and xj. And then if I consider the eigenvalue and orthonormal eigenvector, that is, I say there I had lambda I ei, here let me have eta I and fi, I from 1 to p. The same way as we had considered the lambdas, I have lambda eta 1 greater than equal to up to eta p be the eigenvalue and orthonormal eigenvector pairs of rho now instead of sigma. I had earlier lambda I and ei, eigenvalue eigenvector pair of sigma. I don't calculate the eigenvalues and corresponding eigenvectors for sigma now. Instead I calculate it for the correlation matrix rho, and then I get this is pairs of rho matrix. Then what is the ith principal component? Let me use the same notation yi for principal component. And then what is the ith principal component? Well, originally if you recall, I had yi is ei times x, ei transpose x. Then now using these notations I should have this as fi transpose z, right? And this is nothing but fi transpose v inverse x minus mu. So this is the ith principal component calculated from rho, right? And if I have to consider the variance of this, well, I consider the variance of sum of the variance. The first point to be noted is this, and then I have the total variation in y, that is sum of variance of y I from 1 to p. There are p of them as before, and then this is nothing but, because I had variance of yi equal to variance of xi, so similarly I should have this variance of yi, these new yi's, their variance, sum of their variances should be equal to variances of zi, I from 1 to p. And what is this? What is this matrix? Actually this is giving me the correlation coefficient matrix, and then what are the diagonal elements? The diagonal elements are 1, so sum of them are actually equal to p. So sigma, everywhere sigma replaced by rho. Trace of sigma, now I have trace of rho, which is equal to p, right? And another point that to be noted is, what is the covariance between yj and zi, as we had considered yj and xi? Well, there it was eij, if you recall, it was eij lambda j by sigma ii. So here it is going to be fij, right, with lambda j is now being replaced by eta j, and sigma ii is now actually equal to 1, because I am considering the rho matrix instead of the sigma matrix. Okay. So we will continue with the calculation from a data, calculation of principal components from data after this. Now we consider the computational steps required for the calculation of the principal components. First we consider a situation where we are calculating eigenvalue, eigenvectors from the sigma matrix, that is the covariance matrix, and next we will take up a correlation matrix as well. So the first example that we consider here, this is the computational steps for calculation of PCs, okay, calculation of or construction of PCs. Now that we know the theory behind this, we actually know that the important information, the important data that we require is nothing but the variance covariance matrix of the original variable sigma. Okay, so from here we can calculate the eigenvalues, eigenvectors, and the principal components also. So that is what matters to me. And then I have the first example, say the example 1, where I have the sigma matrix given to me as 1, minus 2, 0, 5, 0, 2. It's a symmetric matrix. So obviously I know that the data dimension is 3. I have a 3 by 3 square matrix which is symmetric and which is positive definite also, right. So I calculate eigenvalues from here, the 3 eigenvalues, and I denote them as the first one is the highest one in this way. So I calculate the 3 eigenvalues and then I put them as lambda 1 is equal to 5.83, lambda 2 the second 1 in magnitude is 2 and lambda 3 is 0.17, all positive. In decreasing order 5.83, 2 and 0.17. I have to consider the corresponding, calculate the corresponding orthonormal eigenvectors. First I get the eigenvectors and then orthonormalize them to get the orthonormal eigenvectors, and these are E1 is the eigenvector, the orthonormal eigenvector corresponding to lambda 1 equal to 5.83 is this one. It's 0.383 minus 0.924 and then 0. The second orthonormal eigenvector, that is the eigenvector corresponding to the second highest eigenvalue, which is equal to 2. This is equal to 0, 0, 1, and E3 similarly is 0.924, 0.383 and 0. If I know this, I know all the 3 PCs. The PCs are, well, the first one is Y1, it is E1 transpose X. So I know what are the coefficients with each of the X variables for the Y1 for the first principal component. So that is 0.383 X1 minus 0.924 X2. That's all, because the third coefficient is 0. The second principal component is identically equal to the third variable, the original variable X3, and the third principal component is 0.924 plus, sorry, this X1 plus 0.383 X1, sorry, X2. That's the third principal component. And if that is so, I am going to now see that how important these principal components are, how much of the total variation they can explain. So this is the few characteristics that we have talked about. So the first one is the first PC explains how much. Well, it will be lambda 1, which is 5.83 by, that is the trace, the total variation, that is sum of the lambda i's, which is equal to 8. And if I say that's this percentage, in percentage, this gives me 73% of total variation. Fine. One may not be happy with only 73% of the total variation being explained by one PC. So I may not say that I am going to reduce the dimension to 1. Let's see if I consider the second PC, or you can say the first and the second PCs together explain. Well, this is going to be lambda 1 plus lambda 2, that is 5.83 plus 2 by 8 times 100%, and this is equal to 98% of total variation. So this tells me that I can reduce the data dimension from 3 to 2, because I see that the first two principal components, they are explaining 98% of the total variation, and this the reduction of dimension by even 1 degree helps me a lot. I can project this data on an xy plane and I can see various characteristics of this multivariate data, right? And what about the correlation coefficient? I have rho of xi, yk. This is, if you recall, we had used a notation yj, and this was eij, and I have root of lambda j by sigma ii, so that I have rho of x1 with y1 is 0.383, that is, I am considering eij, I am considering the jth eigenvector, that is the first eigenvector, and the first element of that, that's 0.583, and I consider the the first eigenvalue, because j is equal to 1, so that is 5.83, and variance of the first, that is the first element of the sigma matrix, and this is equal to 0.925. This tells me about the relative importance between x1 and y1. Similarly, if I consider x2 and y1, what I get is, that is j remains 1 here, but I is 2. So, I have the first eigenvector, but the second element from it, and that is minus 0.924, the first eigenvalue, and the second element, second diagonal element of the sigma matrix, giving me 5, and that is equal to minus 0.998. I can see that there is a direct relationship between x1 and y1, the first variable and the first principal component, whereas there is a negative relationship between x2 and y1, but nevertheless the importances are really high. They are high in magnitude. One is 0.925, another is minus 0.998. What about the third one, x3 with y1? Well, we have to consider the third element of the first eigenvector, and that is equal to 0. So, there is no degree of association between the first principal component and the third original variable. Okay. So, in this way we can, if we want to go to the second principal component, if we stop at the first principal component, we need not go to the correlation coefficient between the xj's, xi's and y2, but if we want to retain y2, we should ideally, because only when the first two are combined we have 98% of variability explained, and then one can also consider the calculate the correlations between xj's, the different xj's with y2. Let us take up the second example, and here we work with the, we will take a smaller matrix and work with both the dispersion as well as the correlation matrix. So, here first consider this is case A. I have sigma is equal to 1, 4, 4 and 100. That is my variance covariance matrix, and my correlation coefficient matrix, well, we can write it later on when we consider case B. And what we have from here is the eigenvalues. From the sigma matrix, I have two eigenvalues, lambda 1 and lambda 2, and these are 100.16 and 0.84. The corresponding orthonormal eigenvectors are E1, this is 0.04, 0.999, and E2 is 0.999 minus 0.04. So, then I consider y1 and y2. y1 is nothing but I have to consider E1 prime x, so which is 0.04 x1 plus 0.999 x2. E2 is 0.999 x1, just the reverse relationship, and then minus with the negative sign here, and minus 0.04 x2, right. So, then y1 explains how much of the total variability? It explains the first eigenvalue lambda 1 by the sum of it, which hardly makes any difference because I have 100.16 and 0.84 added to it, making this as 101, and this times 100%, that is approximately equal to 99% of the total variability, 99% of total variability. And y2 explains the rest of it. So, no need to consider, no need to go to y2. If I consider y2, there is no reduction in the data dimension, and if I consider y2 now, this will explain 100%, but at least from 2 dimension I have come down to 1 dimension. That is the whole purpose, whether it really helps me in data dimension reduction. And then I consider the correlation coefficients also. I have rho x1 y1. This is important, and this is only the eigenvector, the first eigenvector is coming into the picture. This is the Eij part, that is E11 here, and then I have the variance of the first, the standard deviation of the first eigen of the first principal component, that's 100.16 by sigma I, sigma 11, that's 1, and this is giving me 0.04, actually, not 0.04. And what about the correlation coefficient between y1 and x2? Well, this is now going to be 0.99. It's the first eigenvalue 100.16, but now it's the second variance sigma 22, and this is equal to 0.999, right. So, this tells me that x2 is much more important. The degree of association of y1, the only principal component that we are considering, is much higher with the second variable than with the first variable. Perfectly okay, there is no problem with that. So, x2 is much more important to to y1 than x1. Now, what is the true degree of this importance? Is it because of the much higher value of this second variance? So, to look into questions like this, what we should do is actually standardize the variables and work with the correlation coefficient matrix rather than the covariance matrix. Okay. So, that is what we are going to do now. We consider the case B part, where we have the correlation coefficient matrix calculated from the covariance matrix, just by that defining the V inverse, square root inverse of V matrix, and then we can easily get the correlation coefficient matrix, and that is equal to 1.4 I have, and then what is this? Is 0.4 and 1, right. That is, we are considering the standardized variables, that is, the standardized variable z1 is nothing but x1 minus mu 1 by sigma 11, root of this, and z2 is nothing but x2 minus mu 2 by root of sigma 2, and then sigma z matrix is actually the row x matrix, right. This is row x, but I can also have the sigma z matrix, and then this is nothing but this matrix what I am getting here, 1, 0.4, 0.4 and 1, right. And then I calculate the eigenvalues eta 1 and eta 2 from this row matrix, and eta 1 turns out to be 1.4, eta 2 is 0.6, right. And the eigenvectors, corresponding orthonormal eigenvectors f1 prime and f2 prime also have to be calculated. This is 0.707, 0.707, and f2 is 0.707 with minus 0.707, right. And then we have y1. Let us see, that is the first thing that we are going to check. y1 explains, well, what is y1 and y2, that is trivial, we need not write, but let us write here also. y1 is nothing but, if you want to write in terms of z1 and z2, I should write it ideally as 0.707 z1 plus 0.707 z2. These are to be replaced by x1 and x2, and y2 is 0.707 z1 minus 0.707 z2, and y1 explains, and ideally then further you can write this as 0.707 x1 minus mu 1 by the element of the first element of the sigma matrix, that is 1, and you have 0.707 x2 minus mu 2 by second diagonal element, that is root 100, and in this way. Okay. So, y1 explains what percentage of total variability? It explains its own eigenvalue, its own variance, which is 1.4, divided by the total variability, which is sum of eta 1 and eta 2, that is 2 times 100%, and that is equal to 70% of total variability. And if I consider y2 part of it, it explains if the rest of it, right, because y1 and y2 will together consider the total variability. Now that is what we see here. The difference here, if we work with the covariance matrix and the correlation matrix. When we had worked with the covariance matrix, we saw that y1, the principal component calculated from the covariance matrix, explained 99% of the total variability. But here when we consider the correlation matrix, we see that y1 explains only about 70% of the total variation. And let us look into the correlation coefficient part also, where we have correlation between, if I have to consider the correlation coefficient of, this is rho y1 with x1, well, I have to consider the first element of the first vector of the f vector, that is 0.707, and then we have to consider the root of the first eigenvalue calculated from the correlation matrix, that is going to be eta 1, which is root of 1.4, and then the variance, the first variance of x1, this is, well, this is actually equal to z1, right, and the variance here is nothing but 1. We can calculate this to get what is the correlation coefficient, and similarly I can have what is correlation coefficient between y1 and z2, right. So this is going to be the Eij, that is, I am going to use the first element of the second vector, that is again 0.707. I will consider root of 4 and 1 here. The interesting thing to see here is that y1 to z1 and y1 to z2, the degree of association is same, because I have the same value coming here because of the fact that E11, right, E11 is equal to E12, and I have the same eta I value coming here, and z coming now from the correlation matrix have equal variances, which is equal to 1. Okay. So that is precisely equal, rho of y1 z1 is equal to rho of y1 and z2. Our next example will be computation of Pcs from data matrix. In these examples, what we had seen was that I did not have the data matrix, I only had the population variance covariance matrix given to me. That was good enough for me. I calculated the eigenvalues, eigenvectors, and then the principal components, and I then also talked about how much of the variabilities are getting explained by the principal components, and so on and so forth. But in reality, what we are going to have with us is actually the data, the information on the multivariate data variables, and we are going to calculate the whole sample covariance matrix from the data and proceed for calculation of eigenvalue and eigenvector from that variance covariance matrix.